So I'm Heiko Baltzer. I'm director of the Institute for Environmental Futures at the University of Leicester. And as it happens, I'm a Gemini. So the project that I'm leading is funded by UK Research and Innovation, and it centers on the development of self-learning digital twin technology for sustainable land management. So I want to acknowledge this is part of a bigger teamwork that we are doing together with the universities of Loughborough and Bristol. And we are working on two applications primarily. I'm going to talk about one of them today. Before I go into the application, I want to just briefly touch on what environmental digital twins actually are. We've heard in the Gemini framework that was presented earlier that actually digital twins can include a lot of different components. They can include, in the case of environmental digital twins, components like surface models, land surface models, Earth observation data from space or from drones or from other instruments. High-performance computing platforms, cloud deployment is usually used. Data visualization elements have to be thought about, interactive tools. Stakeholder engagement, absolutely fundamental. I keep saying without people, a digital twin is not a digital twin. So we need to think about who's going to use this and how is it actually going to change the world. Machine learning data assimilation also. And then all of this feeds into what a digital twin actually can offer. And digital twins can offer a variety of different things. We can integrate models and observations. We can actually provide predictive capabilities, facilitate change. Ultimately, digital twins are only useful if we want to use them in decision making. And so the two different application areas we are working on, Leicester is working on one of them, Loughborough on the other, is on agricultural greenhouse gas emissions in the UK. About 11% of all our net greenhouse gas emissions in the UK are coming from agriculture and land use. About 7% come from beef, dairy, and sheep production. That's Loughborough's work. And about 4% come from drained peatlands and crop production. And that's the Leicester University part of it. How does this happen? Peat soils, when you lower the water table, start mineralizing, and the organic carbon in the soil is being mineralized and released as carbon dioxide to the atmosphere, so thereby actually hindering the net zero transition that we are legally obliged to in the UK. To illustrate this, we've been measuring carbon dioxide emissions at peatland sites for a long time using these types of instruments, eddy covariance flux towers. They basically show you how much carbon dioxide is going between the land surface and the atmosphere on time steps of about 15 minutes. So you get a very detailed picture of how the environment is behaving. And what we can find here is that semi-natural fenland site on peatland is actually a sink of carbon dioxide over the course of a year. A restoring fen that was taken out of agricultural production some time ago is a source of carbon dioxide, but the biggest source of carbon dioxide is the agricultural fen that is still in crop production. And that is because actually there is a lot of peat mineralization going on and there is not enough uptake of carbon dioxide from the plant growth going on. So we've been working on a decision support tool in the form of a digital twin that we want to make available to farmers and that we want to make available to policymakers for the purpose of deciding how we can change our land use patterns in those areas of drained peatlands. Now, you might ask yourselves, why are we actually not just reflooding the whole place? If peatlands are naturally wet, we could simply turn everything into a wetland. That seems an easy option, but actually when you think about it, about 40% of all our potatoes in England come from that area and of our vegetables. So for food security reasons, it's not an option to just restore everything to wetlands. We need to find more sustainable agricultural practices that deliver on food security at the same time as on carbon dioxide emission reductions. And also at the same time, we want to make sure that farmers have still got a livelihood and can carry on farming. So it is a really, really fiendishly difficult problem we're trying to tackle. And I think digital twins are fantastic technology and have a lot to offer for this purpose. So here's a model we've been working on, and it's an Earth observation-based model that uses satellite data from the Sentinel-2 mission, European Space Agency mission, and from Landsat, which is a US mission. And we've been working on actually quantifying the net ecosystem exchange. So that is how much carbon is going in and out of the land surface into the atmosphere and back. Plants take carbon dioxide out of the atmosphere during plant growth. And at the same time, the soil and the plants are respiring carbon dioxide back into the atmosphere. So what really matters is the balance of it, and that's the net ecosystem exchange. Our Earth observation model essentially tried to quantify this, and it uses a number of different characteristics. The input data are listed there, but I'm not going to go through them in detail in the interest of time. But here's basically how we trained the model. So we had this field station that I showed on the photograph earlier, the flux tower, that measures the carbon dioxide flux in and out of the land surface. And around this, we've assumed a circular footprint, which is a simplification, but seems to be working well enough. And we related this to the satellite measurements around the location of the flux tower site. With this, we've been training a machine learning model using a Python script. And we've been trying this out on 4 different farming locations where we have flux towers. The accuracy of those models that are purely based on the satellite information around the flux tower location sites actually show you that we can see here the pulse of the carbon fluxes, and this responds to the season. There's seasonality going on, so each of the peaks is one growing season, basically. This is the terrestrial ecosystem respiration, so that's the carbon going into the atmosphere from the soil and the plant. And at the top, the engine farm plot is showing the gross ecosystem production. That's the carbon taken out of the atmosphere through the crop growth and plant growth. And so we can see the machine learning models based on the satellite data do actually a remarkably good job at simulating this very complex and expensive and laborious flux tower instrument that we currently rely on. So that's encouraging. We can model what the flux towers see from space. Now, the other advantage that has, of course, is the flux towers are in one location, and you have to have a team of people maintaining them, collecting the data, analyzing the data. Whereas with the satellite data, we can automate the processing. And so what we are doing here, we are interpolating the measurements to the other areas around the fields. From satellites, we get nice images. So we have spatial data, temporal data that we don't get from the flux tower data that are currently being used for monitoring the carbon dioxide exchange. That allows us to go to regional scale predictions. We can go to field scale predictions. And as a farmer, you can select your fields and basically say, well, what's going to happen on this field? And how did the carbon dioxide flux behave for one crop type or another crop type? One of the latest things we are working on right now is a physics-informed graph neural network. That's the self-learning part of the model. The physics-informed part of it basically means that we are using the Joules crop land surface model. That's the community land surface model in the UK that predicts the carbon fluxes. But it is too complicated to use it as part of a digital twin in itself because it takes a few days to run a simulation. So we've been working on a machine learning emulator of Joules crop. And that does the same job, but based on a machine learning model that is pre-trained on Joules simulations. And it cuts down the processing time to a few milliseconds. So actually, it allows us to incorporate the functionality of Joules crop into a graph neural network. The physics-informed part is the really interesting and exciting part of the digital twin work at the moment, because there are a few of these that have been developed. The physics-informed graph neural networks that are out there all are based on quite simplistic systems. And we are trying to use this for the first time in earnest for a very complex environmental system, an environmental digital twin. So the physics-informed part basically says, well, if we get the new data in, if we get the new observations into our digital twin, is our model still fit for purpose, or does it actually fail to represent those new data? And if it does, can we make the model better with a new set of observations? So it can suggest modifications to the machine learning emulator models to mirror the system as it evolves in a much more realistic way. How can this be useful? First of all, we want to go forward in time with our simulations, and we all know that climate is already changing. We have a lot more extreme weather than we used to have. And so there is a big question around the Joules crop simulations and the model simulations currently. Are they robust in future climates? Honestly, nobody has tried because we only have one planet, so we don't have sets of repetitions in different environments. We're about to find out how good those models work under future climates. I think the self-learning component in the digital twin can potentially give us a handle on changing environmental conditions and actually help us keep the model adapted to new climatic extreme weather events. So the components we have in our digital twin include the Joules crop model, community model that's parameterized for different crop types. And that can tell the farmers basically, how does the choice of crop type influence the carbon balance of my field over the growing season? We are using daily meteorological driving data that comes from the UK Centre for Ecology and Hydrology and the Met Office. We are using the land use, soil moisture, satellite data, together with a priori information on farming practices that the farmer has to enter into the digital twin. Weather forecasts going forward could be feeding into it. Flux tower data are being used for training the model, and Earth observation data streams. We're using the Earth observation both for model validation and observations and for actually predicting the carbon dioxide exchange. All of this goes into the digital twin, which is here in the center of the slide. And then all of this then feeds into the digital twin predictions, which ultimately we are hoping will be helpful to farmers to bring down the carbon emissions from their farming practices and to policymakers in designing effective policies for the drained peatlands in those areas. So to conclude, a digital twin mirrors the physical environment based on continuous data streams such as Earth observation and meteorological data. The insights gained from the digital twin can lead to actions that change the physical twin or the environment. In our case, that's what we're ultimately aiming for. And self-learning digital twins are able to discover new equations to improve the model of the physical twin. That's the novelty on the digital twin side we're working on right now. Machine learning models enable greatly reduced computational demand compared to land surface models. And if you're interested in finding out more, my email is on this slide, so just take a photograph if you like, drop us an email, get in touch. We can add you to our community of practice. We are running online events from the project that you're welcome to join. And also I would like to just highlight, without going into too much promotion, there is a conference coming up in December, Artificial Intelligence or AI for Net Zero. If you look at it, it's in Exeter University. And it's a program-wide conference, not just for our project, but actually for all the projects funded under the AI for Net Zero program by UKRI. Thank you very much, and here's a list of our team.
And our next question, I'm going to ask yourself, Heiko, although it probably applies to all of us, is when, in your view, does a model become a digital twin rather than a forecasting model?
So I would say no model is a digital twin. And that's slightly provocative, but I think a model is a part of a digital twin. Models, data, people, and other components have to form parts of digital twins to make them what I understand as a digital twin. So a digital twin is a representation of a real system, of a physical twin, if you like. And a model is essentially a mechanistic representation of our understanding of how the system behaves, whether that's a factory or the environment or anything else. But it cannot actually give us the complete picture without having some data streams also feeding into the digital twin, I believe. So actually the data is really an integral part, from my point of view, of a digital twin, because our understanding may be wrong or it may be limited. And so we need to confront the model with data to actually know how good the model is. And the other essential ingredient, from my point of view, for a digital twin is the user. Because actually a digital twin is not a digital twin without a person using the information coming from the digital twin. The philosophy of digital twins is actually based on them being able to alter the physical environment because people are using the intelligence gained from the digital twins. And so the model itself might generate data, but that's not the same as information. And the decision-making part of it always involves a human user. So a model is essential, but it's not sufficient, if you like, for a digital twin, is my view.
Specifically, what are the top two challenges digital twin ecosystems face with respect to adoption and acceleration?
I would say it's the process of gaining trust in the digital twin. And it doesn't matter whether you're running a factory or a farm or a power plant or a transport network, but before you actually base your decisions on information from a digital twin, you want to be absolutely confident that you trust the information. So that process of gaining trust by the users in what the digital twin gives you, I think, is probably going to take a long time to begin with. Once you have actually had positive experiences with it, I think then that's overcome. But I think I would not underestimate the amount of effort and the amount of time it takes to build that trust.
This is a question for all our speakers. To what extent are you using controlled vocabulary and naming conventions in your architecture? What standards are you using for these terms?
Since the project I introduced is a research project, we tend to rely on the terminology as it is published in the peer-reviewed literature.